All right, today, the main goal is actually to do a bunch of theory. Now, remember, theory is important if you're going to be good at applied stats as well. It helps you see connections. It helps you understand things. And because of that, the goal is it helps you do things that you might not be able to do otherwise if you only know how to do things mechanically speaking. But to motivate us to do the theory, let me remind you of our main application from last Thursday. And that application was to look at the relationship between treasury bill return and inflation rates. Here was the data from the years 1958 through 2013. We've got the inflation rates we thought of as X, the explanatory variable, and the T-bill return we thought of as Y, the response variable. I like using those words, explanatory and response. We're trying to predict Y when we know X. We're trying to say if we know the inflation rate, or at least if we guess the inflation rate, say for the coming year, can we guess the treasury bill return? And the regression model does that in what you might call a purely empirical way, right? We're only going based on past data. We're not really thinking about current conditions. We're not thinking about the current economy. We're just using the past data to make predictions. And because of that, it's not going to be perfect, okay? Because of some randomness, because of the way the economy is right now, for example, the regression equation that we get here may not necessarily be a good model for predicting treasury bill return based on the inflation rate this year in particular. We saw the regression output was down here. This was the spreadsheet output. Let's go through it again. Review. Multiple R. That is again called the correlation in simple linear regression. It generalizes to something else in multiple regression. It's a positive 0.694. The fact that it's positive means the regression line has a positive slope. Here's a square, which I've said is a better measure of the strength of the linear relationship. You can see it's pretty close to 0.5. You might think of this as a typical kind of example of a moderately strong linear relationship. Don't worry about the adjusted R squared at the moment. The standard error, 2.14, I have talked about last week. Let's go ahead and show you what it refers to in the book. It is referring to an estimator for sigma squared. It's this thing here, S squared, or sigma hat squared, is SSE divided by n minus 2. That would be the variance version. The regression standard error would be the square root of this. It's an estimator for sigma squared. I'll remind you what sigma squared is in detail later, but just a brief reminder, it's a measure of the variance in the model, the variance of the errors, which also corresponds to the variances of the Y values for any given X value. That's a real brief reminder of what that is. This is an estimator for it. And its square root is called the regression standard error. That's what this thing is here, 2.14085. N is 56. There's 56 observations. We're again still skipping for the moment this ANOVA table. ANOVA stands for analysis of variance. This will become pretty important for us, but not today. Let's focus down here. First of all, on the coefficients. The intercept is self-explanatory. That is the intercept of the regression line, 2.3027. That's the observed value. That would be what you would label little b sub 0. Capital B sub 0 would be the estimator, the theoretical estimator that is a statistic. This is its observed value based on a random sample. I'm saying random sample. You might argue it's not really a random sample because we're doing it every year for the past number of years. I guess again, it was 1958 through 2013. Not really a random sample in the usual sense, but when you're imagining the population to be, say, all possible in years worth of inflation rates and treasury bill returns, you know, you might call it a pseudo random sample. It's effectively a random sample for the future. You don't see the word slope, but this number here, 0.703075, is the slope. It's labeled with the variable name, the inflation rate. That is going to be the slope. And the regression equation is going to be then 2.3027 plus 0.703075 times x. And then you could use that. To, for example, predict T-bill return in the current year. The current year is 2022. The inflation rate is high. What did I use? 7% last time. Let's pretend it's going to be 10%. Take 0.703075 times 10, plugging in x as if it's got a percent sign. In other words, don't convert that to 0.1. Sorry about my cold. Don't convert that to a 0.1 here. These percentages are not converted to decimals. Plus 2.3027, 9.33 would be your estimate for the treasury bill return. Will that happen? I'll almost guarantee no, right? Based on the current environment, and I looked things up last Friday, I think, and I saw the treasury bill returns are in the ballpark of 1 or 2%. I don't remember for sure exactly. I suppose we can look them up right now. Current treasury bill rates or yields. Okay, still less than 1% for a 3-month treasury bill return. Okay, so they're going up because they are raising rates, the Fed, but they're not likely to fit up to this prediction, even if inflation continues really high, even if it goes up to 10% for the entire year. So you do need to think about practical interpretations of this. Does this really fit the current situation or not? Or do I need to adjust my model? And probably we need to adjust the model in some way. What are these standard errors? Those are standard estimates of standard deviations of sampling distributions. B0, capital B1 and capital B0. Writing these things down. I'm saying these without writing them down at the moment. I will write them down. Are statistics. They have distributions. They have sampling distributions. And based on the model, they end up being normal. You read about this, right? Real complicated derivations, which we're going to go through today. And it's worthwhile to go through today. For their distributions, one thing about their distributions is they're normal. That's actually the easiest thing to prove, that the distributions are normal based on facts from chapter 7. With a certain mean and a certain variance. Square root of the variance is the standard deviation of the sampling distribution. These standard errors are estimates for those standard deviations of those sampling distributions. These t-stats and the corresponding p-values, which you can see are very small, are really ultimately testing whether the population slope and intercept are 0 or not. That's what they're really testing. So whether the population slope and intercept, beta 1 and beta 0, are 0 or not. And you can see the p-values are very small. We would reject that null hypothesis that they're 0. We also have confidence intervals to estimate the parameters. This one for the, was this the slope? Yep, that's the slope estimate, confidence interval. And there's for the intercept. These are 95% confidence intervals, as you can see. Any questions about that? We want to estimate population parameters as usual. Beta 1 and beta 0 in this case. But we want to go even further than that today. We also want to estimate the mean of y when we know x and a predicted value of y when we know x, not just with a point estimate. All right, now let's get into some of the theoretical details. So take a breath, take a deep breath. We're about to do some pretty intense stuff here, but I think this is worthwhile. And so I'm going to go through it. It's not easy, but I want you to do your best to pay attention, and I want you to do your best to say, you know, if I had to, I could force myself to do this without help from the book. I might be unsure if I'm doing it right or not, but I could try, and maybe a colleague in the workplace can try with me, and we can compare answers and see if we're doing it right or not, find our mistakes. Maybe we could do simulation to test if it seems to be right or not. That's probably what we'll do on Thursdays, some simulation. So let's just jump right into it. Let's think first about the statistic to estimate the population slope. So again, here's the estimator for the population slope, beta 1. Get your symbols right. Beta 1 is a population parameter. It's a fixed number, a fixed but unknown number. Does anybody know what beta 1 is? Only God does. Okay, no human will know what beta 1 is, even after the statistical study is done, right? You never know what population parameters are exactly. You're trying to estimate them. Capital B1 is what we call it. And it's worthwhile to remind you how I write these things at first. In its simplest form, capital B1 is SSXY over SSXX, where SS stands for sum of squares. The textbook only uses a single S. I've said this before. I like using SS's, probably on exams. Well, if I write any exam questions, the final exam might be just questions from the book. But if I write any exam questions, I will probably use SS. The bottom of the fraction truly is a sum of squares. And by the way, by convention today, to save time, I'm not going to bother writing I goes from 1 to n. Convention. All summations go from I equals 1 to I equals n. Though I will use an index of summation, I will use subscripts x sub I and y sub I to emphasize those are quantities that depend on I. SSXX is a sum of squares xi minus x bar quantity squared. SSXY is not technically a sum of squares, but we use the notation anyway because it's kind of analogous to what we have here. It's a sum of products xi minus x bar squared times yi minus y bar squared, but since we're doing the theory, y is a random variable. Use capital letters. Y is a random variable, so use capital letters. Our perspective matters. The perspective is we're imagining the x's to be fixed or known, not random. Like pretending I know the inflation rate for the coming year. That's pretending, all right? We're assuming we know that. And the y's depend on the x's, but they depend on the x's with some randomness. You might say there's a deterministic part to how y depends on x. That's the regression line itself. And then there's some noise. There's some a stochastic part, randomness. Okay, it's good to remember this. It's also good to remember what this equals. After some work, the numerator can be written. And once again, I'll write it as the book does, n times the summation of little xi times capital Yi minus the product of the summations, the summation of little xi and the summation of capital Yi. Product of those two summations, maybe you want to use parentheses for emphasis, divided by something similar in the bottom, except the capital Yi's get replaced by little xi's. So you really end up with n times the summation of little xi quantity squared minus the square of the summation of xi. Okay, just reminding you of stuff you already know. Here's something new. Also, after a little bit of work with summations, you can write this in yet another way. We'll leave the denominator the same, but we will rewrite the numerator in this way. Summation of little xi times or minus x bar times a plain capital Yi with no Yi minus Y bar in parentheses. Why can I do that? Is that okay? I claim it is okay. I claim it still gives you the same thing. What am I basing that on? I'm basing on one of these properties of summations, the second one, in fact, that you can actually get rid of the minus Y bar when you multiply. Weird, but true. You can verify it. We've got so many other things to derive today that I don't want to take the time to do that. But it's something you can do. The key is to replace Y bar with what it equals. The sum of the Yi's divided by n, expand and do some simplifying. These are the same, as surprising as that seems. I mean, all these things are a little surprising, I think, that these work. You verified on homework number 1 and 5, I believe. Okay, I still have to grade that. Sorry, I'm behind. Number 2, something similar. That's what I'm using here. And it's fortunate that that works because it does make things easier here. Yeah, thanks for squaring, yeah. It's fortunate that that happens. It does make things easier here. I'm about to do some more simplification of this, more rewriting of it, in a way that's a little strange, but still valid. You know, this thing in the bottom of this fraction is just a number. It's not a random variable. The thing in the numerator is a random variable, right? The x's are fixed, the y's are random variables. But that's a number. I'm dividing by that number. That's the same as multiplying by its reciprocal. I could bring it out front like this. Say it like this, with maybe parentheses like this for extra emphasis. That's just a number. Dividing by a number, dividing by 10 is the same as multiplying by 1/10. And being a number out in front of a summation, I can use the distributive property effectively to bring it inside the summation. This is where it gets a bit weird. I can bring this number inside the summation and even write it as a multiplication here at first. Lots of parentheses. I don't really need the complete outer parentheses, but I'm kind of doing it for emphasis. And then, hey, once again, I'm multiplying by the reciprocal of the number. That's the same as dividing by a number. So what I'm trying to get to here is that I can ultimately write B1 in this way. Summations within summations. Yes, sorry, I keep forgetting it. Being so careful on everything else, but I'm forgetting those squares. Weird, but it's okay. Of course, I could replace this summation with another symbol. I could replace it with SSXX if I wanted to. Is that worthwhile? Well, I think I'll remark it with a different color here. This is the same still as SSXX. Now take a step back and think about what we've got here. This is a linear combination of the y's, of the random variable y1 through yn. I could write this as C1 capital Y1 plus C2 capital Y2, etc., through Cn capital Yn, where C sub I, say, is little xi minus x bar over, okay, for short, SSXX. Linear combination, linear combination. Hey, we like linear combinations, especially when it's a linear combination of independent random variables. Are these independent? What do you think? They gotta be, right? I mean, we wouldn't be doing this if they weren't, probably. But why? Are we just assuming they're independent? Well, effectively, when we assume the capital EIs were independent, that's where the independence assumption comes in. Capital E, what were the capital EIs? That was the simple linear regression model. We assumed each yi, which represents really a condition, an observed value, a conditional random variable, I should say. When you know x equals xi, and you want to model what yi does, what y does that, you can write it this way. We shorthand the notations of this. We're assuming it's a linear function of xi, beta 0 plus beta 1 xi, that's why this is linear, plus some error term, capital EI, where that's assumed to be a random variable with a normal distribution that has a mean of 0. Sometimes these EIs are positive, sometimes they're negative. You want to sort of imagine half and half. So the mean of each EI should be 0, and the variance is sigma squared, y sigma squared, that's just what we call it. It's a variance, why not call it sigma squared? And we assume each EI is independent. E1, E2 through En are all independent. We make that assumption right there, and that implies the y's are independent. So yes, it is essentially an assumption. And why is that good? Well, we don't need the independence to compute the expected value. Linearity of the expected value operator works even when the variables are not independent, but we will need it to help us compute the variance. But before we compute the expected value and the variance, we should remark that B1 is normal, because you got a linear combination of normal random variables that are all independent. B1 is going to be normal. B1 is definitely normal. What justifies that? You could use the fingerprint theorem, moment generating functions. Was an exercise actually in chapter 7. Distribution of linear combination of independent normally distributed random variables. Got n independent random variables. Y is a linear combination of them. Y will be normal. And its mean will be the sum of the means. We're about to do that effectively. And its variance will be this linear combination of the variances. We're about to do these things, though, in the context of regression, it gets trickier to deal with these summations that you see. What is, or what are the expected value of B1 and the variance of B1? You would hope, think about what we hope with estimators. You would hope that this equals something you're familiar with, something simple, something you've read about even, if you did the reading, something that even if you didn't do the reading should make sense. What would you hope that that equals? What is B1 an estimator for? Beta 1. You would hope its mean is beta 1. Hope it equals beta 1. That would mean it's unbiased, right? Our old friend unbiased. You read about this. You should have read about this. You know that's true. It will. What does this equal? That's not so clear. And it's not so clear even what you hope it equals. Though you would hope it's a consistent estimator, you'd hope it be something that gets small as the sample size gets large. I guess we could say we hope that. I'll just say that verbally. So, okay. Let's get into it here. Expected value of B1. Here's B1 as a linear combination. The expected value of such a linear combination is the corresponding linear combination of the expected values. I can effectively write the same thing here, except replace yi with E of yi. I guess I'm going to write SS of XX, sub XX there. E of yi. All right, what do you do with this? I guess we have to figure out what E of yi is. Got a guess for that? Without looking it up? Here's a hint, it's got betas in it. It is related to this equation again. What's the expected value of yi? It's the expected value of this whole thing. That's a constant. What's the expected value of ei? Said it a few minutes ago. Zero. Expected value of a constant is the constant. Beta 0 plus beta 1 xi. Hey, yeah, that's the same as mu. It's the mean. This is beta 0 plus beta 1 x or xi. That's a yi. This has got to be an xi. We're hoping, remember, we're hoping this equals beta 1. So we're hoping that the stuff involving beta 0 cancels, I guess. I could distribute this through the parentheses there. And I could then write two summations, couldn't I? I have the sum of this times that plus this times that in parentheses. And let me rewrite the first summation a little bit. Beta 0 over SS XX xi minus x bar plus summation for the second one will be beta 1 over SS XX xi minus x bar times xi. And the fractions in each case are constants that can be factored out of the summation. We're hoping this all simplifies to beta 1. I guess this part better be 0, is it? You're adding up some deviations from the mean. This pretty intuitively should be 0. Is it? Yeah, that was another property of summations. Is it easy to verify? You did it on a homework problem. I hope you didn't find it to be too hard, that one. That makes more intuitive sense. Question?
Why can't you pull out the SSXX when that technically has XI?
It has xi in it, but only before you do the summation. As a summation, it's a constant, just like it was a constant up here. That's it. That's some number. These x's are given. The summation is some number. I could bring it out in front. It's with its reciprocal because I was dividing it. I can bring it back through the summation like this. It is a number. Its formula involves I, but it is a number. And what about this? Does that really simplify to beta 1? If it's going to, this summation better be SSXX, so it cancels with that. Is it? Yeah, it is. By property 4. Right, that's SSXX there. You can write it with just a plain XI there. Property 1's pretty intuitive. Properties 2 through 5 are not so intuitive, but they are worth remembering here right now for the purposes of understanding today. And again, you can verify these symbolically. You can verify them with examples in a spreadsheet. If you want to just believe them more, you can plug some numbers in a spreadsheet and test them. They work. Kind of surprising, but they work. So this is the same as SSXX. So it cancels with that one. And this all simplifies to beta 1. Done. All right, what about its variance? Variance of beta 1, or of B1, excuse me. Got to do the variance of a linear combination. When the variables are independent, as they are here, variance is linear with respect to the summation, though not linear with respect to the multiplication of the constants. But there's still a property it satisfies. You can pull the constants out in front as long as you square them. So we can write the variance as this exact same summation with yi replaced by the variance of yi, and this thing replaced by its square. Based on independence, the thing in front of the yi has to be squared. And for short, I'll use SSXX again here. Nice shorthand. Squared variance of yi. One nice thing that happens here is the variance of each yi doesn't depend on I, unlike the mean. These are constants. These are each sigma squared. The assumed variance of the capital EIs, those errors, recall each EI is normal with mean 0 and variance that we're calling sigma squared, and each yi is beta 0 plus beta 1 xi plus capital EI. So it's going to have the same variance because this is a constant, not a random variable. So yi is normal with this mean and the same variance. We already used the mean in the previous page. Now we're using the variance. Oh, okay, so where are we trying to go with all this? We're trying to see what we can do to simplify this. Simplifies in one way pretty quickly. You can factor the SS sub XX squared out in front of the summation in the bottom of the fraction and the sigma squared out in front. Yeah, it simplifies pretty quickly, actually. And this thing is SSXX. One factor of SSXX will cancel. This simplifies pretty quickly to sigma squared over SSXX, or in terms of summations, sigma squared over the summation xi minus x bar squared. That was easier than the first one was. The mean of B0 is not too bad. The variance of B0 though gets nasty. B0 being the intercept. Before we look at the intercept, what have we just verified? Therefore, here's a summary. B1 is normal with mean beta 1 and variance sigma squared over the summation xi minus x bar squared. And as the sample size gets bigger, the SSXX in the bottom of this fraction will tend to get larger. And that will make this fraction get smaller as the sample size gets larger. Okay, so we got consistency. As long as you're picking the x values so that you don't always pick the mean, at least, so you don't get a bunch of zeros there. Okay, picking a variety of x values, SSXX will continue to get bigger and bigger as your sample size gets bigger and bigger, making this fraction get smaller and smaller. So it's unbiased and consistent. What about B0? The intercept. Well, what is B0? Recall that it's y bar minus B1 times x bar. Remember that? Except now when we're talking about an estimator, a statistic here, we need to use capital Y bar, capital B1, but little x bar. Because the x values are not random variables. So it's going to be normal for sure, because y bar and B1 are normal. Actually, I haven't mentioned that y bar is normal, but it is. It's a mean of normal random variables. They're not all identically distributed. They don't all have the same mean. They've all got the same variance, but not all the same mean. So the mean of y bar is not so clear, maybe. You might guess it's plug in beta 0 plus beta 1 x bar. You might guess that. But should we verify that first? By linearity of the expected value operator, we get that. Linearity. Remember, little x bar is just a number, a constant. It can be pulled out in front of the expected value. Y bar is sum 1 over n times yi. So we can write this as 1 over n times the sum of e of yi. Expected value of B1, we already know it is beta 1. We already know that. Expected value of yi is beta 0 plus beta 1 xi. Break the summation into 2. beta 0 is a constant. This is n times beta 0. The n's cancel. This whole thing is a beta 0. The beta 1 comes out. This is the same as beta 1 times the sum of the xi's over n. Therefore, this is the same as beta 1 times x bar. In other words, yes, I predicted just a minute or two ago the expected value of y bar would be beta 0 plus beta 1 times x bar. The regression equation replace x with x bar. That should make sense. Said that about 2 or 3 minutes ago. And then these two things cancel. So this ends up equaling beta 0, just like you'd hope. Variance of B0 is where it gets hardest. And for sake of time, since we still want to come back to, I think, to looking at the example, let's just look at how the book does it. And say to ourselves, I believe that I could do that. I was forced. Hopefully not forced at gunpoint. Do it if you want, if you value your life. Hopefully not. Variance of B0. B0 is y bar minus B1 x bar. A linear combination. Independence. Okay, can we assume y bar is independent from B1? Hope it's intuitive that you could. The yi's are independent amongst themselves. They're really independent of B1. I guess we're not proving that in any way. And the book doesn't even mention independence, but they're evidently using it to say it equals this. And factor out the x bars and x bar squared properties of variances. Assuming y bar and B1 are independent, they must be. Otherwise, the book wouldn't write it. What's the variance of y bar? Use properties of variances. Again, these yi's are independent, so you have a summation up there. Factor out the 1 over n as a 1 over n squared. By the way, it would have been good for the textbook to use another set of parentheses here, like around this entire thing. Variance of that entire thing. Each of these variances is the same, sigma squared. There's n of them. So this simplifies to sigma squared over n. Hey, that's not surprising. That happened when you have an average, a mean of identically distributed normal random variables in the past. These, again, are not identically distributed. They have different means, but they have the same variance. So it's not surprising that the variance ends up equaling something we've seen before, sigma squared over n. That's a y bar, but what about the variance of B1 and what about this combination? I got to simplify that. Well, plug in the variance of B1. We found that 20 minutes ago to be sigma squared over the SSXX. So if you ignore that x bar squared, that's the variance of B1. But we're multiplying it by x squared and x bar squared, and we're also adding sigma squared over n. Okay, two fractions get a common denominator of n times SSXX. So with the first fraction, I got to multiply the top and the bottom by that summation. The second fraction, I got to multiply the top and the bottom by n to get this. Trying to simplify. In the numerator, both terms have a factor of sigma squared that can be factored out. After you factor the sigma squared out of this one, it's SSXX, which is equal to this fraction. Another one of those properties of summations. It's number 5, I think, the one you proved. And n times x bar squared is this, because x bar squared will be sum of the x's over x over n quantity squared. One of the n's will cancel, but not the square of the summation of the xi's. still over this. But the sigma squared in front, the summations that are squared cancel because you got a plus sign there and a minus sign there. So what's left is this over n, which is just the sum of the xi squareds. Leave the bottom as is. There we go. That's about as simple as it can be. That's the distribution of the intercept as a estimator, a statistic, normal with mean beta 0 and this variance. And that summation in the bottom is SSXX. Purpose of all this, you should have read about that as well. If we talk about it in the spreadsheet, we can understand the spreadsheet output here. We want, for example, to do hypothesis testing and confidence intervals, as we saw in the spreadsheet at the beginning of class. Hypothesis test, for example, about the slope. The most common hypothesis test to do is where the null is that the slope equals 0. Versus either a right-tailed test, a left-tailed test, or two-tailed alternative. Right-tailed, left-tailed, or two-tailed alternative. Actually, I will tell you, most commonly, people just do a two-tailed. And the p-value that was in the spreadsheet by default is the two-tailed p-value. And that actually goes to the philosophy of how to think about p-values when you're doing tests like this. Some people always do two-tailed tests. They always double one-tailed p-value, even if they have a preconceived notion that the slope or that whatever statistic is positive, say, or negative, because they're trying to make it harder on themselves to make a type 1 error. And if you double the one-tailed p-value all the time, effectively always doing a two-tailed test, you're making the p-value bigger and you're going to make it harder to reject the null for any given level of significance alpha. So some people just always do that, and that's what the spreadsheet does by default, is it gives you the p-value for a two-tailed test. If you can reject the null for a two-tailed test, you'll automatically reject it for a one-tailed test. This is the t statistic. Actually, more generally, it's this. For the slope, it's the slope statistic B1 minus the null value. That's not beta 1 to the 0 power. It's beta 1 superscript 0, where the superscript means it's the null value of beta 1. Not 0 power. Divided by what's this? Standard deviation. It's an estimate for the standard deviation of the sampling distribution of B1. It's called the standard. These things are often called standard errors. Standard error of B1. Actually, in the statistical analysis book that I teach out of, I'm not sure if it's the same. It's not the same one that Alk teaches out of. That textbook, which is an online textbook, labels it SE for standard error, sub B1. In that book, they use a lowercase b1, but I think here it probably would be better to use an uppercase b1. What is it? It's an estimate for this, the square root of this, the standard deviation of the sampling distribution of B1, square root of the variance. Square root of sigma squared is sigma. Square root of that is just square root of SSXX. An estimate for that based on a sample would replace sigma squared with S squared. Where what's S squared? What's S squared? I showed that you at the beginning of class. That thing. replace sigma squared with S squared. S itself is called the regression standard error. And this thing that I've just computed now is also called the standard error, but it's not the regression standard error. It's the standard error for the sampling distribution of B1. Standard error of or for the sampling distribution of B1. Excuse me. Sorry. It's an estimator for standard deviation of the sampling distribution of B1. The spreadsheet output gives the regression standard error. We saw that actually, remember that in the big note and the output, it was the top in the top part. There was something labeled regression standard error. We will look at that again. Does the spreadsheet output give this standard error as well? Yeah, it's right here. Standard error for the slope. There's its observed value. Up here, there's the regression standard error, 2.14085. Down here, standard error of B1. Should we try to confirm these things? Let's see here. Let me try to do that quick. Let me try to confirm that these things are right. Okay, how can I do that? Let me use the fact that we saw in the book that S equals SSE divided by n minus 2. Where SSE is our old friend, sum of squares of errors from the first day of regression. Sum of the residuals squared. So many symbols, so many ideas, so many equations, I know. Let's make a column here in the spreadsheet where we square the residuals. Squared residuals. How do we do that? Let's see, do I have the, okay, I've got the slope in cell D62 and the intercept in cell E62. Take yi C2. That's the first observed value y minus what you might call yi hat, predicted value. Use another set of parentheses here. D62 is the slope time, and I got to use dollar signs, $D $62 times xi in B2 plus $D or E $62 is the intercept. Square that thing. Sorry. It's up there. That's the squared residual. Copy and paste that down. the sum of all those is SSE. So F2 through F57. SSE sum of the squared residuals 247.496. Take that and divide by n minus 2. N is 56, I think. Yeah. N minus 2 would be 54. Oh, I made a mistake here. This is S squared. Okay. Back on here. This is S squared. Sorry. And then S will be the square root of S squared, of course. Square root of this. 2.14085. Yeah, we saw that number before. 2.14085. Right there. So what's SEB1? I've got to compute SSXX as well. Oh, let's see. I need another column. SSXX. I got to do the squared deviations of X values. X's. X's are in column B. Their mean is not computed anywhere, but I can do it here. Mean of the X's is in cell B60. My purpose here is to compute SSXX. So I'm doing those xi minus x bar squareds. Add those numbers up. There we go. I want to see the standard error of B1. That'll be S divided by SSXX, or square root of SSXX. 0.0099 or 0.0993. Did we see that before? 0.0993. There we go. It worked. Anyway, you can get the spreadsheet to compute it. You can also just see it in the regression output in the spreadsheet. So therefore, either way, you should be able to do it either way. You should be able to do this test. This fraction ends up being a t statistic with n minus 2 degrees of freedom. I'm not going to prove it's a t statistic with n minus 2 degrees of freedom. The book does describe why on the previous page. So you can compute p-values using that t statistic with n minus 2 degrees of freedom, not n minus 1. You can also compute a confidence interval on B1. Similar kind of formula as before. T statistic with n minus 2 degrees of freedom. That thing next to the t is SEB1. You can do it for the slope too, or the intercept too. There's your t statistic to test whether the intercept is 0 or not. There's the confidence interval. When the textbook says, when a homework problem says, test for a significant regression, as I believe they do in some problems, like 17, test for a significant regression at the 5% level of significance. What do they mean? They mean do a hypothesis test on the slope, not the intercept. Is the slope 0 or not? And it's two-tailed. If you reject the null, that the slope is 0, then you're saying the slope is non-zero, then you're saying the regression is significant. If the p-value is less than alpha, you're rejecting the null that beta 1 is 0. You think it's non-zero. That means, yes, the test is significant at that 5% level. I also want you to be able to do a few other things that I haven't had time to talk about yet. Computing confidence intervals for a mean and something called a prediction interval for y. How can you do that without me talking about it? Because there's formulas in the book. Just use the formulas. The confidence interval for the mean is this formula. They're complicated formulas. Where what's mu hat y given x? It's what you get when you plug in x into the regression equation. There's your t critical value. There's your regression standard error. And is the sample size this SXX? That's SSXX. X minus x bar squared. That's to give a confidence interval for the mean of y when you know x. Just use the formula with n minus 2 degrees of freedom for the t critical value. And you should be able to compute a prediction interval. A very similar formula, actually, except there's a extra 1 under the square root, whereas back here, this one did not have an extra plus 1. And also, instead of a mu hat, you have a weird looking thing, a y hat given x. Guess what? Mu hat and y hat, those are both computed the same way with the regression equation. Because remember, at the beginning of chapter 11, the authors emphasized that regression equations are used for two purposes, both to estimate individual values of y and means of y when you know x. The mean approach really is more valid, you might say, but people use it to estimate individual values of y. What's a prediction interval? Prediction intervals are confidence intervals. They are. And we still have levels of confidence, but we call them prediction intervals because they're meant to predict individual values of y. And it sort of just distinguishes them to estimating means. People do use them for prediction, like predicting the T-bill return, for example. But they really are confidence intervals and they have levels of confidence. Okay, so I haven't gone through the derivation of those. You could certainly do that. I think probably we will not do that together on Thursday because I think we'll focus more on simulation and other things in chapter 11 and maybe even start chapter 12 a little bit on Thursday. Have a good day.